Look closely at where a heavy locomotive actually touches the rail. It relies on an incredibly tiny patch of bare metal. If you isolate that point of contact, the footprint supporting all that steel shrinks down to roughly the size of a dime. On that single dime, an entire locomotive balances, dragging miles of heavy freight cars behind it. This data visualization compares that scale to a standard truck tire. The truck relies on a massive footprint to grip the asphalt, yet it struggles to pull a single trailer up a steep hill. So why design a machine that intentionally touches the ground as little as possible? In the early 19th century, engineers looked at this exact lack of friction and mathematically calculated that smooth wheels on a smooth track would simply spin in place. They were so certain their calculations were correct that they nearly forced the industrial world to abandon the plain wheel entirely. The rail system actually began centuries earlier in the 1600s in the muddy coal mines of northeast England. Miners laid down simple wooden planks along the ground so their horse-drawn carts could roll out the heavy coal without sinking deep into the earth. Wood decayed rapidly under the constant stress, so by the 1760s, mine owners began capping the planks in iron and eventually casting the rails entirely out of metal. It is easy to assume the modern global standard of iron and steel track was adopted simply because the materials are highly durable. The actual physical advantage was the extreme drop in friction. An iron wheel gliding over an iron rail meets almost none of the resistance created by pulling a cart over a dirt road. Early operators didn't realize they had stumbled onto a major physical advantage. They simply noticed that using metal on metal allowed a single horse to haul loads that would have normally required a dozen animals. By the early 1800s, steam engines were finally getting heavy enough to move along the track and pull loads. That new weight triggered an industry-wide panic about grip. An engineer named John Blenkinsop ran the calculations. He concluded that a smooth iron wheel driven by steam power would act exactly like a car tire trapped on a sheet of ice. In 1812, Blenkinsop patented a solution. He built a custom locomotive that drove a cogged wheel directly into a specialized toothed track. It worked, but installing custom teeth across thousands of miles of railway required immense structural complexity and massive ongoing maintenance costs. In 1813, William Brunton proposed an even more extreme alternative. He designed the mechanical traveler, a locomotive equipped with jointed metal legs meant to push it forward along the ground like a horse. The walking train experiment ended violently in 1815. The experimental boiler exploded during a public demonstration, sending high-pressure steam and shattered metal directly into a crowd of spectators. With the leading designs of the day relying on expensive cogs or failing mechanical legs, the future of the railway appeared trapped. A fundamental misunderstanding of physics had convinced early builders that smooth wheels were a mathematical impossibility. A collier manager named William Hedley suspected Blenkinsop's calculations were entirely wrong, and that the heavy rack rail was solving a problem that didn't exist. In 1813, Hedley built and tested a locomotive named Puffing Billy. He designed it completely devoid of teeth, cogs, or metal legs. The engine drove smooth wheels directly on smooth rails. It successfully pulled loaded coal wagons straight up the line without slipping a single time. This diagram illustrates the newly proven physics concept known as adhesion. The sheer downward weight of the locomotive forces the smooth wheel into the rail hard enough to create kinetic grip. That immense downward pressure perfectly compensates for the total lack of surface friction. It converts the engine's dead weight into forward motion without spinning in place. The absolute lack of contact and friction that engineers initially feared was the exact mechanical property required to make a global rail network possible. Today, that dime-sized contact notch is the foundational physics principle powering modern, continent-spanning freight logistics. There was a brief historical period where some specialized transit systems transitioned to rubber tires to gain specific operational advantages. The 1951 Paris Metro, for example, utilized rubber to achieve faster acceleration and better grip on the city's steep underground inclines. But rubber hits a hard limit of high friction resistance.
It cannot compete with steel's extreme low-friction efficiency when moving heavy tonnage over long distances. That loud metallic screech of a train rounding a curve is the audible friction of this 200-year-old physical dynamic. Every time a heavy freight train pulls out of a yard, it relies on that same tiny point of contact proven 2 centuries ago. It is a system built on a physical reality that our own intuition once insisted was impossible.